Alright, welcome back at YouTube. So we are going to continue our discussion on this black body emissive spectrum. So next thing we want to know, one of the most common things we want to know, is what is the wavelength or frequency or wave number where most energy is emitted. So this is very important, okay? Very important. So why is that? It's because we can find out the primary mode of emission when it comes to radiative heat transfer. So for example, which spectrum are we talking about? Maybe let's say the sun is emitting mostly visible light. A hotter star can be emitting more of a UV light, or it can get so hot that it starts to emit very much X-ray kind of dominant spectra. How do we actually take note of this? Well, so what we do is to simply at whatever fixed temperature, at a fixed temperature T, what is the frequency? So the basic idea is to do a differentiation partial by partial nu of EBVT equals to 0. Alright, so that's all we are doing to find like the minimum point. If you take a look at the graph, okay, a black body spectra will look something like this. If it's in terms of wavelength, it will have this hyperbolic, I think it looks hyperbolic to me, that kind of a shape. And you can see the top is where the gradient is, of course, 0. Okay, and all we have to do is to differentiate this expression with respect to the this frequency. Yeah, so if we know already, we can actually take out the constants 2 pi and h, and somehow we can solve this numerically, and that will give us the answer. Let's see how the textbook actually does it anyway. So if we see the textbook, what they do, okay, first of all, they take it a step further. So instead of having this this expression as is, they're going to differentiate in a slightly different way. I mean, the concept behind it is still the same, but let's follow it step by step. Firstly, they plug up the hole, so to speak. They plug up the knowledge gap. They tell you what the E beta lambda actually looks like, the emissive power using the wavelength. So what they assume is that we have normally, if we have constant refractive index, so that these terms actually disappear, these terms here actually disappear, and then we are just left with this. Oops. So we have the E beta nu, eta, and E beta lambda. So this is what we get. All right. So this is where we are. Okay, hopefully all the expressions are more or less correct. Okay, so we have a c square, a fair bit of c's on top. Okay, the c's actually cancel out, and it should reduce to something like this. Okay, and yes, I think I made a mistake. Actually, E beta lambda should not have this minus sign here. So if we take a look at this relation here, it says that EB dV equals to minus E beta lambda d lambda equals to E beta eta d eta. So actually E beta lambda should not even have this minus sign there. So again, I have to take this out. Yep, that's just a correction from the last video. Okay, but this kind of stays the same. So it's just when we isolate out E beta lambda, we have to do some changes. But other than that, it's pretty much the same. So when simplified, we get this. And why can we say the refractive index is constant as a function of wave number? So this is not always the case. So they say it's very true for vacuums and ordinary gases where n equals to 1. And for some parts of transparent media over large parts of the spectrum, for example quartz, between the wavelength of 0.2 to 2.4 microns, this assumption is acceptable. Otherwise, you have to do all this messy different derivative. Okay, so just to take note, it's not always the case. Okay. Not always the case, but true for vacuum and gases. All right. Yeah. So that's not always the case. And what kind of mathematical tricks did they use to do this basic differentiation? So, in fact, they did something like this. All right. They did something like this. Okay, I'm going to speed this up. I'm not going to do the derivatives one at a time. So I'm not going to simplify this expression, but rather I'll just type out whatever is here. T lambda equals to 2 pi h c naught square over n square lambda to the power of 5. Then you have this exponential here, which I can copy over because there's no need to waste time. So yeah, I'm just going to put that, and that's the exponential that's inside. We don't actually see any changes. There we go. Now it's like that. What did they do to do this derivative? And anyway, they used they would have done it with respect to wavelength, something like this, right? Okay, so there's a very neat trick they did. So consider this. Oops, wrong one. I have to close this up. I'll consider this, yeah. So this is equation 1.13. Alright, this is equation 1.13. Now what they do is to collect, divide both sides by t to the 5. Alright. Okay, so we divide both sides by t to the 5. Alright. And we also divide both sides by and then we divide both sides by n cubed. Oops. Why are we doing this? Okay. So we're going to put n cubed here, so I'm going to change this to, oops, excuse me. Sorry about that. Anyway, we do this very conveniently so that we can group the terms. We do this so we can group the terms n lambda t together. So right, we want to group the terms n lambda t together. And for constant refractive index, we can say these two are pretty much constant. But this becomes a convenient mathematical expression for us. So I'm going to put C naught on top, and I'll put n lambda t at the bottom. I'm going to put this here. Okay, n lambda t to the power of 5. So n lambda t to the power of 5. Perfect. And that's what we do. And now we see that everything else is constant except for this term n lambda t. So instead of differentiating with respect to let's say lambda alone, we can change n lambda t. So we are going to set this n lambda t, okay, and we're going to put this here, and we want to set this to 0. Okay, so setting this to 0, okay, it's yeah, challenging in its own right. Okay, it's challenging in its own right, but there's a simple result that comes out. I'm not going to do the differentiation. It basically says the equation ends up like that. Okay, n lambda t max. Okay, when we set it to 0, we find the maximum. When we set the derivative to 0, we find the maximum, whatever this value is. But yeah, whatever this value is, but we find that for a fixed temperature, this corresponds correspond to the maximum energy emitted for a particular wavelength, or rather it corresponds to the corresponds to the maximum energy emitted for the particular wavelength. So yeah, so basically we find that this holds constant for all black bodies. Holds constant for all black bodies. And if I'm not wrong, this should be called Wein's displacement law. Okay, I'm gonna put this inside the journal here. Alright, so this thing, you solve it numerically, and then we'll find that this actually holds true. This is based on refractive index of the medium it's in, and lambda and T max. So this is Wein's displacement law. Alright, and yeah, this will give us the maximum, the peak frequency, the peak wavelength for a particular temperature. Okay, the peak wavelength for a particular temperature. So yeah, we have Planck's law over here. So this Planck's law is the most accurate. Alright, Planck's law is based on quantum physics. These were based on more classical mechanics, which we will not talk about here. This was just some history. So we do some example 1.1 is just, for example, if the sun is 5777 K, what is the lambda max of the sun? It is 50 microns. Okay, it's just a substitution, and nothing really much to do about that. So that's all for Wein's displacement law. We can go on to move on to other discussion thereafter. So this is basically what the black body emission pattern is like. So Planck's law describes black body emission. Wein's displacement law describes the maximum wavelength, the wavelength for which maximum energy is emitted in the Planck spectrum. It's a black body. So this only applies to black body. If there's some other bodies, we will need to see whether it applies the same way. Alright, but this is the most simple spectrum to get. Okay, so I'm gonna stop here. I'm gonna see you guys next time. Bye bye.